Thanks for joining us today. I'm Chris Ruoff, the publisher of Charged. Today's webinar is about optimizing safety and reliability of EV battery packs with thermal management and sealing, and it's brought to you by Elkem Silicones. After the presentation, there will be a Q&A session. Please submit any questions you have at any point during the presentation by clicking the Q&A button on your screen. The slides and a recorded video of the presentation will also be available on demand after the presentation is completed. A follow-up email will be sent that contains those links. Please welcome the webinar presenters from Elkem Silicones, Catherine George and Chris Helt.
Thank you, Chris, for this nice introduction. So, good morning and good evening, everyone. Thank you for joining us today. We will talk about EV battery pack in terms of safety and reliability. We aim to show through application understanding how we can help to develop customized silicone solutions. Before jumping in this topic, we would like to introduce ourselves to you.
So, ladies first.
Oh, okay. So I'm start. My name is Catherine. I'm working in silicones with Elkem Silicones for more than 20 years. I started by working in R&D department, developing new silicone materials, especially elastomer formulation, and made application support for customer. And now, since 3 years, I moved to marketing on the dark side of the force. Chris, what about you?
Thank you, Catherine. And thank you, everyone, for joining the webinar today. I'll briefly describe my background. I have about 17 years of silicone R&D experience, specializing in developing new silicone formulations for customers in markets ranging from long-term implantables to electric vehicles and everything in between to fit customer needs. Realizing that a material selection goes far beyond the product data sheet, we aim to show through application understanding how we can help to develop customized silicone solutions. In today's agenda, we will review the role that Elkem plays in electric vehicles. We'll then talk about some of the challenges for battery designers, things like thermal insulation of the cells and packs, battery pack protection against environmental factors, as well as thermally conductive materials, which are necessary for fast charging applications. We'll then get into an analytical approach to thermal conductivity measuring in a case study that follows. We will then talk about battery pack assemblies, looking at both the interior and protection of cells from the inside, as well as protection from the outside, i.e. environmental factors. We will finish with some concluding remarks and then have some time for Q&A session afterwards.
Let's start with a few words about our company, Elkem, and what we are doing in the EV market. Elkem is a Norwegian company with more than 110 years of history as a technology provider. In 2011, Blue Star Group acquired Elkem, and the Blue Star Silicones became Elkem Silicones. Elkem has a global presence with 27 plants worldwide. The headquarters is in Norway. There is more than 400 R&D people in Europe, China, and USA. We are in total 6,200 employees for a total operating income of 2.59 billion euro in 2018. As you can see on this slide, we have a strong footprint in Europe, but also in Asia Pacific, and also in Americas. This allows us to follow our customers' expansion in all around the world and secure the supply by multiple sourcing. Elkem has 4 divisions. The first one is foundry. Then you have carbon division, silicone material, and silicones. The 4 divisions are working for the EV market. Foundry division propose additives for steel industry that are used to produce electric motors. Carbon division provide graphite for the anodes of the battery cells. Silicone Material Division provides silicone for the anodes of the battery cells. The last division is Silicone Division, and we are an integrated silicone manufacturer thanks to the silicone material that provides us the silicone, which is the raw material for the silicone manufacturing. And the Silicone Division proposes several solutions for the EV application, like thermal management of the battery pack, protection of sensitive electronics, and high voltage cables. Now, if we focus on the battery value chain from raw material to the end use, Elkem is an actor in two elements of this chain. First of all, in the battery cells, with carbon division and silicone material division. We provide the graphite and the silicone for the lithium anode. And the second element is in the battery pack, with the silicones division for thermal management, protection, and module assembly. Beyond the battery pack, silicone are also used for sealing, bonding, encapsulating, and damping of electronics. For example, in PTC heater with high specific glues that have high thermal resistance, power module with high purity gel, typically low ionic content, and this gel have extreme good resistance in thermal cycling and vibration. Battery pack with thermally conductive material or insulating material, depending on the choice. Battery assembly with sealing options. Sensors with potting materials. High voltage cables. And e-motor and inverters with sealing solution. Until today, more than 360,000 electric vehicles are on the road with our battery packs protection and battery assembly solution. Beyond this number, more vehicles utilize Elkem Silicones with electronic protection and cable solution.
One of the most critical performance and safety components of electric vehicle design focuses on the battery. Technologies that aim to improve these aspects also require a full system review to accommodate and validate for use. It's critical for these challenges to be addressed during the earliest phases of development to avoid costly redesign or product launch impediments. At the core of the battery design is the cell. No matter what type of cell pack configuration, isolation from cell-to-cell thermal transfer is very important. In order to protect neighboring cells, this interstitial space must provide a low flame propagation to prevent thermal runaway. To improve efficiency under heat generation due to fast charging or heavy discharging, conductive heat transfer can be optimized in silicones. And finally, compatibility and efficiency of the system with environmental antagonists, such as temperature extremes, ensure reliability and long product life. In the first study, silicone foam is used in the battery pack to thermally isolate cells from one another on the inside, while isolating and insulating the pack from outside elements. In the event of a thermal runaway, silicone can offer fire protection by insulating neighboring cells from heat and provide a suitable path for the venting thermal propagation event to take place without leading to a chain reaction inside of the pack. Due to its thermal insulating qualities, silicone foam improves high thermal stability, leading to a longer lasting, higher performing battery pack. Another advantage to a foam system is its low density attribute, which yields a low weight material. This is a factor as energy consumption is directly related to overall vehicle weight. So to illustrate the level of thermal insulation possible with silicones, we designed a study in which we made a approximately 1/4 inch thick slab, and these were molded from these 3 different materials you see on the first column: a silicone adhesive, a syntactic silicone foam, and a blown silicone foam. The slabs were placed on a hot plate, and the temperature of the hot plate and slabs were measured directly using a thermocouple plate and allowed to reach equilibrium prior to measurement. These 3 columns represent 3 different hot plate temperatures. Here we have 22 degrees C, 52, and 102 degrees C. For a temperature of 52 degrees C on one side of the silicone, the opposite side of the silicone was kept at a temperature below 40 degrees C in the case of the foams. And at 102 degrees C, the opposite side of one of the foams, the blown foam in particular, saw a temperature of only 53 degrees C. That's approximately a 50% reduction in temperature. In the first application case study, we looked at the use of silicone in the battery pack. We characterized filled, unfilled, and foamed samples. On one hand, there is a trade-off between thermal conductivity and density for thermal dissipating solutions. On the other hand, the processing parameters, density, and hardness can be optimized for thermal insulating solutions. Now, let's look at technology used to protect the battery pack from environmental factors. These environmental factors, like dirt, moisture, and temperature, can all lead to premature failure of a battery pack. Extreme temperatures, ranging from the Arctic conditions seen in Norway to the Mojave deserts in Arizona, cannot impact the temperature of the battery module. Otherwise, performance and lifespan of the cells is greatly reduced or compromised. In some extreme cold conditions and environments, a heater may be required just to maintain the optimal temperature for best cell performance. In addition, component vibrations can also reduce the lifespan of the battery pack. But with proper sealing and encapsulating of the battery module, these factors can be greatly reduced or even eliminated, leading to a more reliable system. Foam silicone solutions can come in both a blown and a syntactic foam. A blown foam uses gases produced by a 2-part reaction to generate voids, while a syntactic foam uses micronized hollow beads added in the manufacturing of the 2-part system to yield a low-density cured material. While the blown foam has the lowest thermal conductivity and lowest density, it can require fine-tuning to be used in a manufacturing setting. The 2 blown foams seen here generate gas to achieve their low density. It is critical to have a good process control in order to achieve this consistent density and physical properties, especially in a manufacturing setting.
In fast charging, but also during the use of the car, the key parameter to control is the cell's temperature in order to optimize its life cycle and its efficiency. Another solution for the thermal management is to use conductive silicones. They are also used around the battery pack for the thermal dissipation. By incorporating high amounts of thermally conductive fillers, silicone improve heat transfer from the hot devices to the cooling system, which ultimately extend battery life and performance. Even highly filled silicone demonstrates good wetting and flexibility, which are important characteristics for good thermal transfer and stress dissipation. This is an advantage of the silicone compared to other polymers that are used to produce thermally conductive materials. Today, we offer thermally conductive silicone ranging from 0.4 to 3 watts per meter Kelvin, and are willing and able to provide customized solutions. We also propose grades with low volatiles content to respect automotive standards. A common question is silicone pad or liquid silicone? What is the best option to dissipate heat from battery modules to cooling plate? With silicone pad, as you can see here, on a visual aspect, everything seems good. But if we magnify this interface, this section here, we can observe that the pad doesn't cover the surface smoothness, and some air gaps are still existing, which is not optimal for the heat transfer. Now, if we applied a liquid silicone between the battery modules and the cooling plate, the wetting is very good. And even after magnifying this area at the interface, all the air gaps are filled with thermally conductive silicone to ensure the most efficient heat transfer. The liquid version is the best choice of material for heat transfer. Elkem provides several families of material with thermally conductive performance, like coating, adhesives, or gap fillers. Today, we offer thermal conductivity from 1 to 1 watt, from 1 to 3 watts per meter Kelvin, and more in the future with electrical insulation properties. The harness can be modulated from soft material to harder ones, depending on the applications. This product offers also fire resistance and thermal stability.
With the abundance of solutions for thermal managing solution, the important factor lies in the ability to accurately measure the property that is best represented in the application. The method used to measure thermal conductivity can strongly influence the results of the reading, configuration of the constructed part, and the best representation of heat transfer will help model the dissipation of heat through the battery pack. To illustrate the importance of application-specific testing, Elkem technical staff wrote this white paper. Within it, several testing standards and associated equipment were used to evaluate the thermal conductivity of silicone elastomers. One particular electric vehicle customer had challenges in understanding which test method best aligned with their application. Elkem Silicones selected BlueSil ESA 7712, a low viscosity 1.5 watt per meter Kelvin thermally conductive potting material, as a base material, and worked directly with the customer to identify the testing correlations between 4 different test equipment. The hot disk TPS system, seen here on the right, utilizes a nickel spiral sensor element in the shape of a double spiral that would be seen right underneath this metal plate right here. The TPS sensor acts both as a heat source for increasing the temperature of the sample and as a resistance thermometer for recording the time-dependent temperature increase. In this table, we've summarized the results of all 4 types of equipment used to test one formulation. All results were performed under triplicate testing with the same material while varying test equipment, test method standard, and test engineers at global laboratories. Results from the ThermTest hot disk, TA instruments guarded heat flow meter, Xintian instruments DRL3 all showed results with a standard deviation of 0.01 watts per meter Kelvin using ASTM and ISO standard testing. However, the outlier test results yielded from the C-Therm TCI device under ASTM D7984 were greater than 20% deviation from the other equipment and test method standards. Fortunately, the ThermTest hot disk test method aligned closely with the application for the EV customer, so it was chosen as the correct method for estimating thermal conductivity. Further, it was important to understand the variance in materials within one test method. Table 2 shows the comparison of measured increased filler loading levels of BlueSil ESA 7712, yielding thermal conductivity using the established direct thermal conductivity measurement of transient plane by the hot disk method. The results showed consistent outcome with a standard deviation of 0.01 or approximately 1% of triplicate testing. In the end, it is always important to collaborate with the customer to determine the best material and test method in order to achieve consistent and reliable data.
The last challenge that we would like to address is to seal the battery pack assembly. Typically, a lead seal is created to either adhere the lead to the module housing or dispense a seal which adheres to one surface and provides environmental protection from the other surface. This allows for reworking and maintenance to be carried out on the battery pack, like using a dispensable foam in the battery pack. Use a foam-in-place foam gasket, which allow for better sealing of part through low compression deflection. Thanks to the low modulus, this material also provides damping qualities for NVH, noise, vibration, harshness, and as regulation require main benefit for EMI, electromagnetic interference shielding. The table shows two material options for battery pack assembly. The first, dispensable blown foam, provides a low viscosity for processing, which yields a thixotropic bead with a density about 1/4 that of most silicone. In the second row, the Cafaxat series of adhesives provide similar bead dispensing, but with superior adhesion to many substrates. Both systems do not require heat to cure and can be easily scaled with dispense equipment and robotics to a fully automated system. In this case study, silicone foam-in-place foam gasket was developed for the battery case assembly. It was learned that dynamic mixing of a thixotropic foam was necessary to get uniform bead shape and pore size. Through process optimization with dispense platform, a high-quality seal was demonstrated by passing IP68 water sealing test.
So to conclude, silicones provide many advantages for designers and engineers of the EV platform. To achieve reliability and safety with a silicone solution, we have proposed foam and adhesive solutions for sealing the battery pack from outside elements and protecting the cells from damage due to vibration or heat buildup. In addition to the battery pack specific properties, silicones also boast high thermal stability across a wide range of temperature, hydrophobicity, as well as UV and chemical resistance. Also, tailored materials can be made to meet almost any process parameter. We are an integrated silicone manufacturer with a global footprint and have over 40 years of experience in the automotive industry. We have a technical support team dedicated to our customers as well. If you would like to learn more, we have several resources on our website, including the white paper on thermally conductive measurements, ebooks for thermal management solutions, and brochure for the electric vehicle market, like battery, hybrid, and electronics. We realize that a one-size-fits-all model rarely works, especially in emerging markets. Although we have only showcased a selection of our products, We like to work with our customers to better understand the challenges and develop a material that best fits the customer's application. Our technical service team and sales staff can work with you to define the critical parameters and translate this to a formulation that our R&D team can quickly and confidently scale.
Thank you for participating in today's webinar.
We hope that we have shed light on some of the EV components whose functions are critical to reliability, safety, and quality.
And now let's move to the Q&A session.
Great. Thanks for the presentation. At this point, we'll begin the Q&A session. Please submit any questions by clicking the Q&A button on your screen. As I mentioned at the beginning, we will send a follow-up email that contains links to download the slides and video of this presentation. I see we have a few questions already from the audience. Catherine and Chris, if you could begin by reading the question and then answering it, that would be great.
Okay. Maybe one for you, Chris. There is about the cooling properties. If our silicone provide cooling properties or help in cooling of battery packs.
Oh, okay. So this question, I think, is designed really to ask whether or not our products produce active cooling rather than thermal conductivity, which draws the heat away from a certain material to something maybe like an active cooling system or a heat sink. It's important to note that our silicones convey heat with high thermally conductive fillers and do not participate in active cooling. There do exist phase change materials, and they are on the market that perform these functions. This technology, though, however, releases and absorbs the energy, which constitutes the phase change, but many of the products haven't been fully commercialized or are not readily available. In conjunction with the active cooling system, thermally conductive silicones can draw heat with efficient conductive thermal transfer. And so that's really the highlight, I think, of what we're trying to show you here today, is the heat dissipation property. Good, all right.
Thank you.
Yeah, so let's see here, there's some more questions. Okay, I've seen a couple here. Basically, we've shown some videos, I think, that may have sparked some interest in this subject, and regarding dispensing process, this question says, regarding blown foam materials, do you recommend a certain dispensing process? Also, can you recommend a dispense equipment manufacturer?
Oh yeah, good question. First of all, I would like to mention that the dispensing process is really key for a foam to achieve the right performance, like the density and the pore size and the homogeneity of the cells. Our principle is not to force the customer to work with this partner or that partner. We can work with everybody, but we can recommend some partners if the customer doesn't have his own partner for the dispensing equipment supplier. So we have some partners all around the world, in all regions, that we can work together to achieve the best sealing.
Great. All right. So let's move on to another question. Let's see. I've seen this question a lot with manufacturers of cell battery packs. Basically, the question asks, what is the difference between a polyurethane foam and a silicone foam?
Okay. I think in that case, we can compare flexible polyurethane foam with silicone foam. So on both sides, they have the same properties. With the harness, the type of cells, etc. The main difference is coming from the intrinsic performance of the polymer. Like for the silicone, so you have the thermal stability, the fire resistance. The fire resistance is in the sense that the silicone will not generate toxic smoke, in opposite of the polyurethane that generates toxic smoke when it's burning. And so it's a safer product. The silicone foam is a safer product for the application. We have published an infographic on our automotive blog, so you can have more detail in this document also.
Great.
Yeah, I can see also another question about what is the lowest or highest thermal conductivity, what is possible with the silicones. Yeah.
Great question. So there's kind of two parts to this question, obviously a low and a high. But by nature, silicone is intrinsically thermally insulative. Pure polydimethyl siloxane has a thermal conductivity of about 0.18 or 0.2 watts per meter Kelvin. You can compare that to the thermal conductivity of air, which is 0.02 or 0.024, I think, to be more exact. The difference there basically describes the effect that one can see from a low density foam, in that if there's more voids in that foam, you will typically take the thermal conductivity measurement of air with much greater weight than that of the silicone itself. The highest thermal conductivity possible in silicone is fairly tunable, but today it stands at about 8 to 10 watts per meter Kelvin. It's important really though to realize that while high thermal conductivity is possible, there is a compromise that comes along with this high filler content. Once a thermal filler package is identified to meet the thermal conductivity requirement, properties like fire protection, thermal resistance, and property stability over time are retained due to the silicone polymer structure. Other physical properties, however, like durometer, viscosity, and cure kinetics must be optimized basically every time that thermal conductivity number is changed. Also, in addition, raw material costs for these fillers and the additional processing that can be involved can drive that overall cost of the product up. Good, all right. So let's see here, let's find another question. So I see one here about volatility, and I can kind of understand where that's coming from. I think with the safety aspect, a lot of people want to know what is the level of volatiles that you can achieve in your silicones?
Yeah, it's an important question for automotive manufacturer. So in regular thermally conductive material with a standard thermally conductivity that is required in battery pack application, the standard volatile levels, when I say volatile level, it means the sum between the D3 to the D10. When we do that, the sum between the D3 to the D10, we are in the regular material below 0.5%. In the case there is a specific need, we can achieve lower level, typically below 350 ppm for the sum from the D3 to the D10. But of course, this will generate additional costs. So it depends on the application that you need, but we can achieve this low level of volatile in the thermally conductive materials.
Great. All right, good. I think looking at the time, I'm running low, I think, on time. What we'll do though, I think there are some more questions I've seen. Yeah, there are plenty more. So what we're gonna do is we're going to send out emails specifically to those who pose these questions, because we do wanna answer all of your questions and basically answer anything that you have regarding this presentation or further questions regarding our products. So I think we'll stop here, but we will, like I said, answer the emails or in the form of email, the questions that have been asked so far. So unless there's anything else, I think we'd like to thank you all for joining us today. It's a very, very good chance for us to present, and I hope you've taken away some information and hopefully inspired some ideas and things that you can use in your own applications. So,
okay.
Great. Thank you, Catherine and Chris, for the great presentation.